Welcome back. In this video, we are going to learn about fluid properties. Fluid properties helps us to distinguish between one fluid to another fluid. There are several fluid properties. Okay, and in this video, we are going to look into two of those fluid properties which are very important and got a lot of engineering applications. So let us start with this image. You see a lady floating in Dead Sea. She is just floating there and she is able to read a newspaper. Expert swimmers can do that, but this one is very special case. You can, even if you want to sink, it is not going to happen. This is because of a special fluid property, and it has something to do with this fluid property which we are going to discuss today. And let's look into another example. This is about a failure of a bearing at high temperature. You will see that these machineries which operates at high temperature, and especially the rotating components, they fail at high temperature. And this is because of the failure in the lubrication system, and again something to do with a fluid property which gets affected at high temperature. So let's learn a little bit deeper into all these and understand how we can apply it in real world engineering applications. So let's start with the first property, which is density. And you know this, the property density, you will learn it from the high school itself. So what is density? Density is nothing but mass by volume, right? So we know this density, represent it as rho, which is m by v, or mass by volume. So everybody knows this. Or in a more mathematical way, in a more technical way, you can define it as a point function where limit dv, the small tiny volume tending to 0, delta m by delta v is the same. And the unit is kilogram per meter cube. This much everybody should be very much familiar because you have learned it in your school physics. Now let us try to understand it. Okay, this is mass by volume, this is fine. Now let's say in these two examples at STP, at standard temperature and pressure, for water the density is 998 kilogram per meter cube, and for air it is 1.2 kilogram per meter cube. So what does it mean? How do you visualize it? You can easily visualize it. You can just take a box with 1 meter by 1 meter by 1 meter as the dimension. So it's 1 meter cube, and imagine you are filling it with water. So if you fill it completely with water, it is going to weigh approximately 1000 kilogram. It's 998 kilogram, which is basically its density, right? 998 kilogram per meter cube. So in 1 meter cube, you are going to see almost 1000 kilogram. Whereas if you try to fill it with air, it is going to be almost 1.2 kilogram, very less weight, right? So this is how you just visualize density. How one is very dense. Some of these fluid can be really dense. Some of the fluid are, especially gases, are very light, not very dense. Okay, so you understood what is the idea of density. Now let's take this example. You take a glass and fill it with water first, and on the top of that you try to fill oil. What will happen? Will it mix? No, right? So this is nothing to do with density. What will happen is, because of the chemical bonding, the water and the oil is not going to mix together. It is not miscible. It is an immiscible combination. So, and more interesting thing which you need to notice here is, it's not about the chemistry I am talking about. The oil is going to float and the water is going to stay down. What is the reason? And you can add different liquids at different densities, and definitely it should be immiscible. If it is miscible, means it will mix, like you can mix alcohol and water, but the problem is they will they will mix together chemically, so you cannot separate it out. But here they are separated, you don't mix together, so you will see oil floating over water, and that is because the density of oil is much less or relatively less compared to water. That's why it is floating. It's a lighter fluid compared to water. So if you pour anything lighter than that, that again will float over that. All right. So this is why this is very important, especially when you're dealing with multi-phase system, when you're dealing with multiple fluids together and you want to simulate it or you want to test it, you're going to see this feature. In most of the cases, you can say that rho L is nearly constant, or the density of liquid is nearly constant. And when you're dealing with CFD simulation or any analysis, you can treat the density as constant, like water. You can treat it as nearly 1000 and then do the calculation. But we should be very careful when we are dealing with high temperature applications. So there are cases, especially oil and oil system, if you have high temperature, this density can really change. So if you're dealing with cooling off, let's say electric motors, or if you're dealing with some bearing system where you're using some oil, and it can really heat up when you're operating for quite a long time. So in these kind of conditions, the density should be, you should treat it as a function of temperature. The density should be a function of temperature. So the density can really vary with temperature. Okay, and you may have to plot it or use the function when you're doing simulations or analytical calculations or anywhere, wherever you're going to use this density. And in liquid also, there are certain cases where it can be compressible. It can change with respect to pressure also. So for example, density can be a function of pressure and temperature. These are cases where you are going to apply a lot of pressure. So normally when you are applying pressure, let's say this is liquid inside, a piston arrangement, and you're going to apply some force on this or a pressure here, and then you're trying to compress it. If it is liquid, it's not going to compress much, right? It is not going to, the density is not going to change, or it's not going to get compressed. It's nearly incompressible. But imagine you are going to apply a lot of force, a lot of pressure. In those conditions, it can really change. And there are very, these kind of applications are very less, but still there are applications. For example, in fuel injection system, in diesel engines. So you have the injectors and you have the pumps, high pressure pumps, which generates pressure up to 2000 bars. It's really very, very high pressure. And at this condition, 2000 bar or 2500 bar and all, in diesel engines, it is compressible. So you have to treat diesel as compressible in these kind of condition, and then you have to do all the calculations. Similarly, in GDI engines, you are using gasoline. Even if the pressure is like 100, 200 bar, it can be also compressible and the density can vary. Okay, so these are special applications where liquid can be compressible. And also in liquids, in special cases, even if it is water and it is not really compressible, it is not, it's not going to compress much. But if you want to track sound waves, if you want to do some kind of acoustic calculation, let's say cavitation bubble collapse, and you want to track how the pressure wave is moving, then you need to treat the water as compressible. Otherwise, what happens? If it is incompressible, the speed of sound is infinite, right? So you cannot really track it. So if you want to really track, then we have to treat water as compressible. And there are special equations to do that. We will come to that in a short while. Now we have seen that even for liquid, the density is going to change with respect to pressure and temperature. So then what about gases? Definitely it is going to change quite a lot compared to that of liquid. So then we need to understand this compressibility effect a little bit more deeper, right? And to understand that, let us write in terms of specific volume, which is the reciprocal of density, so that we'll get a sense of volume, and it is easy to understand volume, right? When you are compressing something, volume is becoming smaller, right? It's easy to understand. So let us write it in terms of specific volume, which is nothing but volume per unit mass. So specific volume, small v, is a function of, it's a function of pressure and temperature. So it's a function of pressure and temperature, just like the density, right? It can change with respect to pressure, it can change with respect to temperature. Now we can imagine it in terms of volume. You're applying some force and think about the change in volume here. Now we are interested in the tiny change in the volume, the dV, right? So because of this pressure or application of this force, there is a small change in the volume. So to understand this volume, the tiny change in the volume, we can differentiate it. So this is dV, and think about this. This is a multivariable function. It is a function of pressure and temperature. So we have to use the chain rule here. So this is nothing but dou V by dou T at constant pressure dP plus dou V by dou P at constant temperature dt. So this is what our change in volume is. So what is this term? Dou V with respect to dt. And what is this term? The change in volume because of pressure. So this has to do with the change in temperature, which is going to change in the volume. This is called the thermal expansion coefficient, and this one has to do with the compressibility. So you can write it as the thermal compressibility. It is written as tau, which is minus 1 by V dou V by dou P at constant temperature. And this is the isothermal compressibility at constant temperature. So what about this one? This is 1 by V dou V by dou T at constant pressure, and this term is the thermal coefficient of expansion. Thermal expansion coefficient or volume expansion. This one, as we told, it is isothermal compressibility. Okay, so this is very important to know that your density is going to change with respect to pressure and temperature, and especially for gases. Now imagine an application where you are going to use compressors, you are going to simulate compressors, you are going to do something where there is a high pressure application, plus there is a high temperature application. The pressure is changing, the temperature is changing, then your density cannot be constant, right? You need to change with respect to pressure and temperature. So for gases, especially when you're dealing with air, you will use density as a function of pressure and temperature. And what are you going to do when you're doing a simulation, let's say a CFD simulation? You will use rho as ideal gas. Then it is easy, it will take care of, it's a function of pressure and temperature. So you can write it like, what is ideal gas law? P is equal to rho R, which is specific, and the absolute temperature. So with this, you will take care, this is the ideal gas law, you will take care of this compressibility effect and the thermal expansion effect. So this is very useful. You can just use it, in you're using ANSYS Fluent or any tools, you can directly use this. And for the case of liquids, in liquids you can use another equation. I would like you to explore about this. This is called as Tate's equation or modified Tate's equation. So this is what you will use to account for the compressibility effect and take care of this density, which is going to change with respect to pressure or temperature. So this is about density, right? But there are different fluids, right? It is not just air or water. There are plenty of fluids. And in engineering applications, you may be asked to use some kind of refrigerant, for example, or maybe some other chemical, which is supposed to be used for some heat exchanger or somewhere else. So how do you find the property? How do you know the density value? Or even if you know the density value, how do you know how is it going to vary with pressure or temperature? Or if you don't have any ideal gas law or Tate's equation, if you want to use your own plot, where do you get these values? For that, this is one which you can use, the NIST database. It is free. Go and search in Google. You'll get plenty of the data in the NIST database. The NIST database is the one which most of the engineers and researchers are using for their research work. So I would recommend you to go and explore this. You can get isothermal properties, isobaric properties on many of the chemicals. Many fluids are available, and a lot of properties, not just density or some of these properties, but many other thermo fluid properties are there which can be used for your calculations. Now let's look into the second property, which was causing the problem for the bearing system, right? And this guy is viscosity. So you're familiar with viscosity. You know what is viscosity. You can see the images of two liquids here. One is less viscous, the other one, the honey, or a thick fluid, which is highly viscous. So it's very easy to understand, right? Water, it flows very easily, no much resistance. Honey, it flows very at slow speed. It is thick. It is, there's a lot of resistance for its movement. Now, there's something called the dynamic viscosity. So when we say viscosity, normally we talk about dynamic viscosity. So imagine you are running in air, like how you run normally, right? You are surrounded by air and you are just running. And now imagine you are surrounded by water instead of air and you are trying to run. What will happen? Just imagine it. You can already feel a lot of resistance, right? You cannot run as fast as you would run in air. And this is exactly what viscosity does. Viscosity is a property that represents the internal resistance of a fluid to motion. Okay, so it's a resistance. And this viscosity or the dynamic viscosity, it is represented as mu, okay, and the Greek symbol mu. And the unit is Pascal second or Newton per meter square second. And there is another one or another viscosity which normally you use in engineering applications, and this is called the kinematic viscosity. Okay, and it is represented as nu. And usually we use it because it will take care of the effect of the dynamic viscosity and the density. The nu is mu by rho. It is the ratio of dynamic viscosity to density. And the unit is meter square per second. And this dynamic viscosity, mu, is also going to vary with respect to temperature. We should take care of that as well. So it's a function of temperature. So, and interestingly, it is going to be different. The way it varies is going to be different for liquid and for gas. For the liquids, when you increase the temperature, when you heat it, the viscosity goes down. So in the bearing system we saw, right? You keep on increasing. So when it is rotating, when there is it is going to generate quite a lot of heat, and what happens? It is going to reduce the viscosity. And whereas in the case of gases, it's the other way around. When you heat it, when you are going to increase the temperature, the viscosity of gases increases. It has to do with the kinetic molecular theory. it is going to have a lot more random motion, and this is going to help in increasing the viscosity. So for the gases, the viscosity increases. So again, we need to consider this, especially when you are using gases or air and all in high temperature application, in compressors or any compressible flow application, the temperature is going to change. So you have to make sure that your viscosity is also going to change, just like the density is changing. Another important point which we have to discuss here when we are discussing about the viscosity is the Newton's law of viscosity. Tau is equal to mu du by dy. So the shear stress is equal to the dynamic viscosity multiplied by the velocity gradient. How do we get this equation, right? How can we derive this equation? Let's do that. This is very easy, very easy to follow as well. So let us consider there is a flat plate which is stationary, a stationary plate, and on the top of that there is some liquid which with a thickness of L. And above that you have another plate which is going to move now, and we are going to apply a shear or a shear force in the tangential direction. If you are applying a normal force, means in the normal direction, but it is a tangential force, it's a shear force. So you are going to apply a force, and this plate is going to move at a velocity capital U. Now let's push it. Yeah, so the plate has now moved, and so how much distance it moved? It moved in a time dt. This is the time which we have used, a very small time, the delta t or dt. In this small time, the distance ds is the velocity multiplied by the time. So it is capital U multiplied by dt. This is very clear for us. And another thing which we know here is it got deformed. This got deformed by an angle d theta. But we are not interested in the deformation here, or the strain here. We are interested in the rate of strain. In fluids, we know the shear stress is all about the speed at which the strain is happening, the rate of strain. And we also know that the velocity at the bottom, right, on the plate, it is u equal to 0 because it is a stationary, and because of no slip condition, we are going to have a velocity as 0 for the fluid. And for the fluid or the liquid, when the plate is moving, the velocity on the top of that is going to be, again because of no slip condition, it is going to be u equal to the velocity of the plate, capital U. So if you imagine, or if you make an approximation of the velocity profile as a linear profile, we will get something like this, right? One side u equal to 0, other side u equal to capital U, and it is varying linearly. So we can write down uy, the velocity profile, is equal to capital U by L multiplied by y. It's a equation of line. And what is interesting for us here? What is interesting for us? We are interested about shear stress. Shear stress is proportional to the rate of strain. So the rate of strain, how fast or what is happening to this angle, the deformation, with respect to time. Now we need to connect this d theta, the deformation, with respect to, along with the velocity, or how is it going to connect with the velocity. And you can write from here, we can say du by dy is equal to capital U by L. This is easy, just differentiate on both the side. Du by dy is equal to capital U by L. So we got this relation here. And d theta, you can approximate it as tan theta, right? For a very small angle, we are talking about very small angle. Here everything is exaggerated a little bit, and this angle is not going to be that big, it's going to be very tiny. So with that small angle, you can say d theta is approximately tan theta. And what is tan theta here? This is ds by L, right? So ds by L is nothing but u multiplied by dt divided by L, and U by L, we have a relation here. So the U by L, you can write it as du by dy multiplied by dt. So from this, d theta by dt is equal to du by dy, right? And now we have to put it here. So we can say tau is proportional to du by dy, or the velocity gradient. And the proportionality constant here, we can say tau is equal to mu times du by dy. And this proportionality constant is the dynamic viscosity. Okay, and any fluid which obeys this law, shear stress is equal to mu times du by dy, these kind of fluids are called the Newtonian fluids. Not all fluids are going to obey this law, the Newton's law of viscosity. Only those fluids which are going to obey this law is called the Newtonian fluids. And there are many other fluids which don't obey this law. But fortunately for us, the air and water, which are usually the engineering fluids which you are going to use, they are Newtonian, and it's very easy for us to analyze that. Based on the Newton's law of viscosity, we can classify fluids into different types. For that, let us plot rate of deformation on the x-axis and the shear stress on the y-axis. Okay, so if it is the tau is 0, so that means only on the x-axis, this is the ideal fluid, and this is ideal. Okay, so there is no fluid like that. And you can have in the same way, if you are considering only the y-axis, it's an ideal solid, and there is no solid like that. And our Newtonian fluid, this is the one which is going to vary linearly. When you are plotting tau and rate of deformation, Newtonian fluid is going to be linear. It's going to vary linearly. So Newtonian fluid examples are water, air, most of the engineering fluids which we are going to use for engineering calculation and our day-to-day activities, it is Newtonian. This is very good. But there are different types of fluids. Now imagine, the curve is slightly different. So how can you read this curve? So that means for a smaller rate of deformation itself, you need a higher shear stress. And then after that, it comes down. You need less shear stress for more deformation or rate of deformation. Can you imagine some fluids for this? For example, paint. Okay, so if you are into painting anything, all right, acrylic painting on the canvas or on the wall, you can see that initially you have to apply a little bit more pressure, more shear stress. And then after that, it goes smoothly. Same for ink. And another example which is interesting is the blood. The blood is a non-Newtonian fluid and it is a pseudoplastic, or it is shear thinning fluid. It is this kind of fluids are called shear thinning fluid. And then we have some fluids which is the other way around, which is the dilatant fluid. This is called the shear thickening fluid. What does it mean? So that means for the smaller rate of deformations or initial rate of deformations, you need less shear stress. And then beyond that, you are going to have higher shear stress. So how can you visualize it? So for example, if you are standing in a beach, right? You just stand in the beach, you slowly will go down. The sand is like that. So that sand in the beach, wet sand is a dilatant fluid or shear thickening fluid. It just goes, your feet is going down. But imagine and now jumping on it. If you apply a larger force, you will not go down. You will just stay there. Similarly, cornstarch. You make a solution of cornstarch and hit it with large shear stress or large force, you'll feel that it's going to resist it. But when you dip it, your hand slowly, it will go in. You can apply this concept for the bulletproof jackets for army. So if the bullet hits very fast, if something is coming very fast, it is going to resist it. Okay. And another type of fluid is the Bingham plastic. So Bingham plastic means they behave like solid for some time, right? Until you apply, there is a threshold shear stress. Until you apply that stress, it is going to behave like a solid. And after that, it is going to behave like a fluid. For example, the toothpaste. So you have to apply a pressure. Initially, it will look like a solid. Now you apply a pressure, and after that, it smoothly goes out, right? It will behave like a fluid. So this is Bingham plastic. So there are different types of fluids, and you need to know what kind of behavior it is, and then accordingly you need to model. For example, if you are interested in simulating or modeling a blood flow, or you are interested in modeling something to do with paint, you have to model it as a non-Newtonian fluid. Otherwise, you are going to get a wrong result. And when we are discussing about the applications, this point, the viscosity changing with respect to temperature, this also need to be addressed. So if you are doing any kind of simulations or any kind of calculations where the temperature is going to increase, definitely make sure that your viscosity is a function, even for liquid or for gas. First thing is you can look into the NIST database and use that function for your calculation. Otherwise, for air, you can use another law, very famous law called as the Sutherland's law. So this is the Sutherland's law is very famous, and you can use it in any CFD software or anywhere. And how does the law look like? So the law is the viscosity mu is equal to mu 0, the reference viscosity, multiplied by temperature divided by the reference temperature. Reference temperature is the temperature at which the viscosity, raised to the power 3 by 2 multiplied by T0 plus a Sutherland's constant S divided by T plus S. Okay, so T0 is the reference temperature. So you can use this law, and the only unknown here is the values, right? Your reference value mu 0, T0, and the Sutherland's constant. And people also use this another equation for the same purpose. You can use C1 T to the power 3 by 2 divided by T plus S. So S is the Sutherland's constant. So you can get these numbers here. You can look into the literature as well. So for air, you have the value for mu 0, T0, S, and also the C1, this constant. So you can use either this formula or this formula, and you can add it as a function in your simulations or wherever you are going to use the calculation, so that you don't use a different viscosity or don't use a constant viscosity. So make sure, especially when you're dealing with compressors, turbines, all these high temperature applications, this need to be taken care. So that's all, and I hope now you know the answer why this lady was floating in the Dead Sea, and the problem which was causing for the failure of the bearing. If you know the answer, please drop it in the comment. That's all for this video. See you in the next video.